All right, so now let's look at another way of improving the performance of a Rankine cycle. This is through adding reheat to the cycle. So one of the big problems with a Rankine cycle is that you can extract so much energy during the turbine process that your quality of the steam is low and you end up damaging the turbine blades. So we could extract the steam early in the process of the turbine and reheat it in the boiler or a second part of the boiler and improve the process. So we have, what really happens is like we run it through the boiler, we run it through a high pressure portion of the turbine. It comes out of this at sort of a mid-range pressure. We'll reboil it here and then take this and go the rest of the way down to the lowest pressure I'm looking for in the rest of the turbine. I really don't require a lot of equipment changes because really this is a change in piping more than anything. So I'm going to take the material through the boiler, but I'm going to have some space left in the boiler. I'm going to send that material in the pipe to the turbine. I'm going to run it through the turbine, but partway through I'm going to put a wall in there and extract this through a little pipe on the side and send it back into the portion of the boiler, run some more tubes through there, and I'll heat it some more, back into the rest of the turbine where I had that other side of the wall, and then I'll have that go through the boiler, or go through and do the work of the turbine. If you look at this as a picture, I'm going to come in here. I've got it set so that at this point I've got state 1 is the inlet to the pump. The numbering is fairly arbitrary. But so if I look at this as being state 1, it goes through the pump requiring some work input, but it comes out as a compressed liquid at a high pressure but low energy. I'm going to add heat in through the boiler, so it's constant pressure going through this boiler, but it comes out with a high temperature and pressure. Goes into a turbine where it loses energy, so it's going to come out at a lower temperature and pressure. But I'm not going to take it all the way to my lowest pressure. I'm going to take it out a little early. I'm going to now reheat that by passing it through another portion of the boiler. So this will be constant pressure, but it's not the same pressure as this one. This is a high pressure. This is a middle pressure. And now then it's going to come out superheated or saturated vapor here, go into the rest of the turbine, do more work, come out as a low energy steam, go into the condenser, heat transfer out, we'll turn it back into a saturated liquid. So our basic assumptions, again, are that all of the heat transfer devices are isobaric or constant pressure. Those little pressure changes across these pieces of equipment are small and really are not going to make a difference in my thermodynamic analysis. Now the boiler and the reheater, I'm going to assume heat to a quality of 1 unless I give the pressure and temperature. The condenser is going to cool to a quality of 0. Always. It's unreasonable to do anything other than that. I am going to work with ideal reversible adiabatic pumps and turbines, which means these are constant entropy processes. And we know that we can use process efficiencies to change that and get rid of the ideal reversible assumption. My net work is going to be the sum of all of the turbines and any pumps that I have in the system. And my heat transfer for the boiler is going to be for all of the various places where I add heat into the system. If I look at an example, this is just a simple modification of the previous example. I'm going back to saturated vapor R134A coming out of the boiler at 85 degrees C with a quality of 1. It's saturated vapor. This time, when it gets to a pressure of 1.5 megapascals, I'm going to extract it from the turbine and send it back into the boiler, bringing it to a temperature of 85 degrees. So at this stage, out of the second part of the boiler, it's going to be superheated. It's going to be at a temperature of 85 and a pressure of 1.5 megapascals. So the first time is saturated, the second part is superheated. And now that I'm going to go through the second portion, the low pressure portion of the turbine, until I reach this low pressure of 1.0164 megapascals, which is going to give me the 40 degrees C saturated liquid that I wanted going into the pump. Let's now look at gathering the data for this. So 40 degrees C and a quality of 0 are known. This was a given value, this is an assumed value, but it allows me to look up the data here. It's exactly the same as it was before. My pump is constant entropy if it's ideal. I'm taking it up to the saturation pressure for 85 degrees C, so these two pressures are the same. It's a compressed liquid. I can't look up data for refrigerant 134 as a compressed liquid. Now, it's going to go from here into the boiler. So this is the exit of the boiler. 85 degrees C and a quality of 1 was my assumption for the exit from the boiler, the first pass. That means the pressure is 2.926, and these are the properties. From here, it goes through the turbine. So 3 to 4 is the high pressure turbine. And it's a constant entropy process. So the entropy at 85 with a quality of 1 is 1.68. So I'm looking for a quality of 1.68 at the exit of this turbine. I also know that the pressure is 1.5 megapascals. That was given information in the problem statement. So with this pressure and this entropy, I can look up this data. Now, it's heated from this temperature to 85 degrees, but it's constant pressure. So that means it's going to be superheated in the second phase of the boiler. But again, I can look up all of the data across here. And now it's going to go through the low pressure turbine where it's going to have constant entropy, but it's 1.81 this time. Okay, it doesn't need to be the same entropy as before, just that it's constant as it goes in and out of a turbine. And the pressure is 1.017 because we need it to be compressed liquid going into the, or saturated liquid, going into the pump. So this means it's going to leave my turbine as a superheated vapor. If I plug these numbers in to analyze all the equipment, the work of my pump stays the same, the enthalpy coming out. So this is V delta P. This is from delta H set equal to this work, gets me the enthalpy coming out of the pump and into the boiler. The enthalpy difference across the first turbine, the enthalpy difference across the second turbine. The net work is the sum of this, this, and this. So 3 pieces. If I were to calculate the back work ratio, we talked about that last week, that's the work of the pump divided by the work of the turbines. Both of them this time. Okay. The heat transfer into the boiler, well, I have 2 stages. I have the high pressure stage and the low pressure stage. I end up with a net for the boiler of 214. And the thermal efficiency is the net work over the total heat transfer in, which is for the 2 stages of the boiler. So 19.4 divided by this 214, and I got 9.1% efficiency. Now before I had 10.2, so this is worse for efficiency. However, let's come back to look at the data. Okay, a couple of things to point out here. First of all, this still has a lot of heat in it. I could have cooled this to a much cooler temperature, okay, or in the turbine, so left it in the turbine longer to a lower pressure and ended up with something where I had used more of the energy. One way to vary that is to change the pressure here and modify this. In this case, I might have taken it out maybe a little earlier. Okay. and I would have had more of the energy to be used in the turbine, the second turbine. And that might have improved my thermal efficiency. But I'm saving the turbine blades. I'm saving on equipment costs and maintenance costs. All right? We have one more video where we're going to begin looking at regeneration. And that will be our last set of modifications for our Rankine cycle.